It's the middle of the night. You're sound asleep, and this happens. You get paged. Something's down. It's 4 in the morning. You start looking into things. You want to see what's going on. You launch your site. Maybe at 500s. Maybe sometimes it works, sometimes it doesn't. Maybe you get timeouts from your backends. How many of you have been in this situation? Yeah. Good times. You start looking into your exception tracker, maybe. You have a lot of apps. Maybe a lot of pieces are moving around to make this work. You have to have a huge amount of knowledge about all of the pieces of your system to be able to even begin debugging it. You might start with your front end, but what systems is that then accessing that might also be going wrong? You have to kind of have this all in your head to even begin debugging the problem. And it's 4 in the morning. You start looking at your front ends. Maybe there's some timeouts. Where are they coming from? What's the back end that's the problem here? You might look at a back end, see something that might be bad user data, bad data somewhere along the line, records not getting created. Where does that come from? How do you know? How do you figure out where this is going? Is there a bug in your code? Was there a recent deploy that might be affecting something about this? Where's the bug? Is it on your front end, your back end, background workers? Could be many places. Is one of your systems down? Maybe one server out of all your clusters. Which one is it? How do you find that out? What if it's a back-end system as opposed to a front-end system? Maybe there are database problems. Again, could be any number of your systems. How do you figure out what the cause is? Maybe you're out of swap somewhere, or you're swapping. So the database is up, but not working well. How do you determine all these problems? So I'm going to talk a little bit about all these things. A couple hours later, you managed to get the site back up. It was painful. It was a slog. You had to figure out a lot of things manually. You might be still dealing with customer requests, but you do get it back up, of course. So my name's Andy Delcambre, like Shane said. I go by Delcambre on the internet, Twitter, Flickr, GitHub, etc. I do live in San Francisco right now. This is from basically my front yard over by Dolores Park. But I grew up in Portland, so I'm kind of native-ish from the area. And I work at Engine Yard. This is based largely on a lot of pain points that we have. We have a relatively complex architecture with our systems, and we often run into exactly the problem that I described at the beginning here. The caveat here is that all the things I'm talking about are things that I would like to do and things that I think that we should be doing at Engine Yard, but we haven't done it yet. So these are all kind of concepts and ideas that I'm thinking about. We're not to the point of actually getting this in production yet. So this problem that we're facing, it could definitely be better. Like we could make the computers work better for us so we have tooling around these problems across the distributed systems that we're talking about here. So mostly what I'm going to be talking about is tracking the requests as they flow through your system throughout your entire architecture, throughout all of your pieces, the pieces of your architecture. And the cool thing about this is that it's really pretty simple. There's only a few things that you need to do to be able to track your requests across your whole system, but the benefits that you get from it are pretty huge. So the first thing we want to do is, at the first point at which a user or an external request hits your architecture, you want to generate a request ID for that connection, basically. This could be outside of your system even at the edge, like a load balancer and HTTP server. There are some load balancers that do that. If you do, that's awesome, and you should use it. Not everyone has that bit in their architecture, and so I'm going to be talking about basically at the first level, it hits a Ruby app and a rack middleware specifically that you could use to generate these request IDs. So a little tiny bit of code here, a rack middleware. This should maybe look familiar. It's a very sane rack middleware initialized with the app, call method. The important bits are down here in the call. So the first thing we're doing is that we're either going to pull the request ID off of the environment as it comes in, off the header. This allows you to pull it off of the initial load balancer if it's being added somewhere outside of your system. But if it doesn't exist, we're generating one. So this is basically, as we pass it along the system, we'll either reuse the one from the previous request or generate a new one. We're taking that request ID that we generate, and we're going to put it into thread local. This means that on a multi-threaded server even, you're still going to be able to keep track of that request ID across your entire request all the way down through your models and everything, which makes it much easier to pass that along further down the chain. This might be a little bit controversial. I think that there's a little bit of problem here with knowing that this string is special, and I'm kind of hand-waving here a little bit in my actual implementation that I'm playing with. This is all abstracted behind a library, so you're not calling the thread local directly. And then the final bit here is we call the app, and then on the way back out to the browser or to whatever is making the call, we add this request ID back into the headers. So that way, if you're trying to debug the system and you make a call and you see errors or you see something strange, you know what request ID that came from. You can see that back in the headers, so you can look it up in the system that's hopefully storing this. So a little diagram here. This is kind of the type of system I'm talking about here. You have some sort of front-end server. This might be handling your JavaScript front-end or something like that. You have some sort of initiator that's happening from outside of your system. This could be a user that's hitting your site with a browser. This could be an API request from another system, another company. Could be pretty much anything, but it's just something that's outside of your system. It's hitting that front-end box initially, and then it can go from there many directions. So this is a very simple thing, maybe 2 backends and some background jobs. But in reality, this will probably be much more complicated. You might have 10 backend systems. Your backends might call other backends. All of those things probably have rescue jobs in the back. But kind of for the purpose of this talk, of a simplified example. And the cool bit is that once we get all of these pieces in this system where we're tracking them, this is basically it. As soon as you add it to everything, you get a huge amount of benefit. So at this point, all we're doing is just setting an ID for every request that comes in from an initiator. So second, we haven't done anything with this yet. All we're doing is basically assigning a request ID and then sending it back to the browser. There's no there yet. So what we want to do is we want to log every request that comes to our system. I'm doing this right now with another rack middleware and logging it in the request. If you're getting a lot of traffic, that's probably not the right way to go. And I'm more interested in the concepts here than the actual implementation. This is probably not the most efficient, but it's the simplest to describe. So again, another really small rack middleware here. I've excised the setup. The important parts here, we're logging the start time and the stop time. So before we call the backend app, we're storing off the local time. We're again pulling that request ID off the thread local that we stored on the other middleware. And then we're generating a sort of JSON object of the whole request. So this is pulling the environment from the initial request and then merging in a few things that we care about. Most importantly, that request ID again. We're also logging the start time and the stop time so we know how long it took and when it happened. This will help us build up some request traces later, potentially. And finally, we're posting it off to an unnamed backend system at this point. This is a little bit hand-wavy at this point. So next, we're still not getting that much information, right? We're seeing all of the requests that come into our system, and this can definitely be useful, but it's not terribly different than a lot of things we can already do. But if we add these request IDs to the exceptions that we generate from our app, then we're starting to get more benefit. So if we have yet another rack middleware, this is some little exception logger, again, excising the setup. And we are, again, calling the app, and then rather than putting this in an ensure block to make sure that it runs every time, we're only rescuing exceptions here. And the important parts here are we're, again, pulling that request ID off, so we attach it to that initial request that comes in. We're converting the exception and the Ruby environment to a hash and the initial request. We could also add a bunch of other things in here. This is kind of a minimal version. Things like business information that might be important. So what user this is, what account this is, and at Engine Yard we have the concepts of environments and apps. So we could put what environment or app this is related to. You could put what server this is, what PID of the backend this is. Lots of information in these requests, which will help with the correlating those errors later. So now what benefits do we get? We're still not terribly different than what we have now. We're still basically going to get this list of exceptions, tie them back to requests. You might get a little bit of benefit if you're triggering requests or triggering exceptions from sort of your model layer directly, because those right now, if you don't tie it back to the request, you're not going to have the request information in your models unless you specifically put it there. So this allows you to get that pretty easily. But overall, we're not terribly different than where we are right now. So let's do it one step further and start adding it to our background jobs. So how many of you guys use Rescue for your background processing? Wow, surprisingly a small number. These concepts could be applied to any background processing system, really, but the important part is that there's something consistent that you use that you can then wrap around to be able to add this request ID through. So the way that Rescue plugins work is a little bit limited, I would say. There are probably better ways to do this, but I kind of stole this from Defunct's Rescue Lock plugin. But basically what we're doing is we're defining a module, we're overriding the onQ method, or we're actually writing the onQ method. This takes the args, so we're going to use this rather than rescue.onQ. We're, again, pulling the thread local off of the, to get the request ID. We're storing that off. And then we're basically just adding that request ID to the beginning of the args list that the job on the other side will be able to pull off. So we're using the normal rescue.onQ here and putting the request ID in. So this all happens in your web side, basically. On the other side, once your job actually picks up that, or once your worker picks up that job, we can use this around perform hook. Again, there's a few things that are kind of weird here about Rescue. But the important bits are that we get the request ID that we set in that onQ method as one of the args, the first arg to the job. We're again pulling the start time off so we can see how long the job took and when it started and stopped again. And then we're building up this sort of object that represents that this job ran. So again, this is relatively limited for the slide, but you can put a bunch more information here. But we are logging that request ID and the start and stop time, the args of the job. The class of the job would probably be good here. And I don't know, any other context that you might have for this job. We're again posting it off to that same backend, so everything will be in the same sort of bucket and we'll be able to correlate across all of those things. The one interesting thing here is that because we're just yielding and there's no way to change the args list from our Rescue plugin or Rescue hook, the Rescue job will actually get that request ID as one of the args. So you have to kind of write your jobs for this. So this is a really simple job that we might be using. The important bits here are that we are extending that request ID class or request ID module onto this class. You need to be able to do that, otherwise it won't work. We are getting the request ID in the perform method, like I said. There's no way to change that right now with Rescue. And then, we're calling the onQ method on the job class itself rather than Rescue. So this is a little bit of a different API. This is kind of how we do it at EngineYard anyway. We have some wrappers around Rescue, so we're always calling onQ on the job method or on the job class. But we're not passing in the request ID here. That gets added by the onQ method directly. So again, back to our diagram. We have these background workers, and now we're passing the ID down to the worker. So now that initial ID that came from the initiator is trickling a little bit down into our system. It's not all the way through yet, but this gets us a little bit more benefit. And again, the same thing as before, it's useful to have all those request IDs and those requests and the fact that we're getting these traces, but if we attach the request ID to the exceptions that we generate and the exceptions that we have on our server side, we'll be able to get even more information. So another little around perform hook. This would probably be the same hook as the last one, but just for the purpose of these slides, separate it out. So we're pulling the thread local off here to get the request ID. In fact, in this one, we can actually get it directly, but thread local to keep it consistent. Imagine that's the library call again. So we're pulling the request ID off. We're rescuing the exception. And then again, we're generating this JSON object that gets served off to the server side to be able to track the args to the job, the exception, the Ruby environment that we're dealing with, and again, most importantly, that rescue ID, or that request ID. So now things get really interesting. This is now we're to a point where we are far beyond anything that we can deal with today, right? So now if you have an exception in your job class or in your job, you can see the initial request that came in, what user generated it, what the input that they entered. Maybe it's a form post with bad data. you can see maybe that there are 2 errors that are the same error that are really coming from both ends of that pipe. So if there's a request that comes in and it fires off a background job and then it ends up 500ing, and then that rescue job also raises, probably due to the same bad data. If you're looking at one, you can see that the other one's there too because they share the same request ID. So this gets really powerful. There's a lot of things that you can do with this that you couldn't do before. And again, we're tying the job back to the initial request. So if we have, again, bad input making it down to the job, or we can see what user initiated this request, or see what maybe some more business logic type stuff, like what environment they're talking about, what app they're talking about, what thing they were trying to deal with that initial request. So we have our rescue jobs now instrumented with these request IDs. There's sort of one more piece to this system, and that's any backends. We have this, like I said, we have the request ID going all the way to the job. Now we want to get it down there. At Engineer, we use Rat Client a lot. How many of you are familiar with Rat Client, or have you even heard of it? Cool. So a few, but not many. Rat Client's really cool. It's written by my friend Tim, who used to work at Engineer, and it basically introduces rack semantics to the client side of the HTTP connection, specifically middleware. So you can add middleware to the connection. It has a bunch of different backends that get run as basically rack apps. So it can use NetHTTP or XCon from the Fog library or a few others. But it's really pretty cool. It kind of has REST client semantics, but you can add the middleware. So this is a sample client middleware for a Rat client setup. It looks basically like a regular middleware, pretty much exactly the same. You're initializing it with the app, but the app in this case is probably a backend that's going to make calls out to the backend server. The call method, similar. We're pulling the request ID off of that thread local again, and then we're calling the app, which is the backend, which will make an actual HTTP call over the wire, and we're adding that request ID into the headers before we send that off. And because this is using the same sort of rack semantics as everything else, if you put the header in sort of rack style with the HTTP all caps, when it comes out the other end, it'll be converted to an x-request-ID, like the normal HTTP header looking thing, which is pretty cool. So kind of the best part about this is that with Rat Client, you can tell Rat Client that you want to use a middleware across all of your clients that you might generate. So every client that you generate after this use call will have this middleware injected into it. So if you're using Rat Client across your whole system, you'll get the request IDs triggering through them without having to modify any of them, which is really pretty powerful. It's pretty cool. So again, back to our initial middleware that I showed sort of on one of the early slides. So if we have that backend that's also using that same middleware, so we're dealing with this thing again, right? So we're pulling it off of the environment, or we're generating. What this means is that with that client-side middleware, we're injecting the request ID into every single request. So if that makes a call to another backend, we're going to pull that off, and we're not going to generate a new request ID, which is pretty cool. And the cool thing about this is that you don't have to have custom code in your backends that differentiate it from a front end. It's the same code everywhere. And if there's a server in your environment that deals with both internal requests and external requests, it'll work in both modes. Our billing app is kind of like this. We make a lot of calls to our billing app to make sure people are paid, that they're generating invoices, things like that. But the customers also go directly to the billing app to see their past invoices, change their payment information, things like that. So this will work in both modes and generate new IDs if someone's coming to it directly, or take the request ID off the API call from the other side. So again, back to our little diagram here. Now we have this initiator, and then we're calling from the front end down to the back end. This could even be inside of a rescue job, because we're just always storing on that thread local, so all the semantics are the same regardless of where you're calling from. But we're passing that request ID to the back end, so we have this tree system all the way through the app. So now what do we get? If we implement these 3 steps across all of our systems, and if you're using sort of a consistent way to make backend calls and it's a consistent way to run background jobs, it shouldn't be a huge amount of code to write. It's mostly just getting it sort of deployed to all the pieces. And if you do these 3 things, and you're logging these all somewhere, you basically get full traces throughout all of your system. You know for every request, all the things it's touching. If you have an exception, you know where that came from and where it's going, what sort of all is around that. And it means that you don't have to know ahead of time, as someone who's looking at the system, what it takes to build every request. So if you get a request in and it's 500 in, you can see that maybe this one's hitting the billing app, or this one's hitting our ticketing system, or this one's hitting our other thing, and you know where to look. You don't have to have that all in your head from the get-go. You also get correlation, so you have more information with each error. You can know, again, specifically for exceptions, where it came from, potentially what user triggered it. You know, even multiple levels up the chain, this could be an exception that's happening in a background worker on one of your backends that was triggered from another background worker on your front end. You can have these chains, and as long as you're passing that request ID all the way through the system, you're going to have the information regardless of where it comes from. We can also see if one request triggered a bunch of errors. So with our backend and front end example, you might have a situation where the backend is 500 in for some reason, but that means that the HTTP call that's getting called from the front end will 500, and so you'll probably raise again unless it's not a very important thing. So you'll get two exceptions that are effectively the same exception, just two ends of the pipe. And if you're keeping track of these request IDs, you'll be able to know that those are in fact the same error. You'll see that they're correlated. So what's really cool about this is that now that we're logging all these requests and all these traces throughout our system, we can do a lot of other stuff with it. We get these request traces. We can see the full stack of our app. If you make an API call, or you make a call to the app, and you get that request ID, you can see the trace. You can see how long everything took. You can see the different time slices of each app that you're dealing with, even the background jobs. You can see potentially why your front end might be slower because it's making 5 calls to a backend, and each one of those is taking a quarter of a second or something like that. This is pretty powerful. This is something I can't do right now, at least not easily. Again, you can see if one backend or one front-end request is firing off tons and tons of jobs unintentionally. You can see that whole list of them, and then maybe that's hammering your rescue servers. The other thing you can do, and this is a little more computationally challenging, but you can roll up those traces and see changes over time. So if you can identify traces that look the same, have the same semantics, you can track them over time and see that, oh, this front end's getting slower. It's gotten 200 milliseconds slower, but that 200 milliseconds is all in this one backend system that maybe needs another server or another scale, but the scale of it needs to be bumped up a bit. These are things that are really challenging to debug right now. You have to do a lot more manual tracing, and this kind of, if you have the right tooling, can be much more visible. So throughout this whole talk, I've been talking mostly about the client side and about the concepts of this, but I have completely hand-waved over where you put all these requests and exceptions. And again, that's partially because it's still a concept idea. I have been playing with some things though. So where do we want to put these? We could put it in something like MySQL or Postgres. There's something inherently wrong with that. It would probably work. But the way that the data is structured with these kind of arbitrary JSON blobs that are going over the server, I think it lends itself more to a document database. Maybe something like Mongo. This is, as I understand it, originally built for kind of analytics tools like this. But you have to still know ahead of time what indexes you want, what things are important to you. So if you're running this for a large system and the business metrics are different for different things, you have to kind of do that all by hand and have to write a lot of maybe MapReduce queries and things like that. So the tool that I've been playing with is called Elasticsearch. How many of you are familiar with Elasticsearch? Cool, that's awesome. Some of you, at least. Elasticsearch is awesome. It's based on top of Lucene, and so it's basically just everything's indexed that you put into it, all of the fields across the whole system, which is really cool because it means that you can query and correlate across any of the things that you put into it without having to write custom code to do that. You don't have to tell it that you want these things indexed. It's really easy to set up. It's in Homebrew. You can run brew install Elasticsearch and it will just work. And it's very easily distributed. I haven't played with this much. Again, I'm not running in production yet, but it has sharding and distribution of the data built into it. So you can have a widely distributed thing pretty much out of the box. And what I love about it is that it has a very sane JSON HTTP API. I took a couple of examples off of their website to kind of just show their example as like a Twitter clone. Kimchi is the guy that wrote it. And so this is basically like just throwing some JSON into this index called Twitter. We have a post date there, and JSON doesn't have a native date type, so this is just a random date string. We have a message, and we have a user. So this is like the most kind of basic example. You can just pass it a search string and do things like show me all the things where the user is Kimchi, right? So this could be useful for us in many ways, but it gets much more powerful than this. So this is an example of give me a date range. So it knows and it can figure out that those timestamps are dates, and you can say, show me all the tweets that happen between these two dates. And you can, of course, build these up as well. So you can say, show me all the tweets that are for a specific user or whatever. So every time, basically, I look at the docs for Elasticsearch, I find more cool things. You can do geoboxes. It knows that if you have like Latin long or geohash coordinates, that those are point types. And you can say, show me all the things that are within this box. I didn't even know it had that. That's cool. It also has things like, they have a query called more like this. So you can basically say, perform a query on an object with just a list of fields that you care about, and it'll show you all the other objects that have that same list of fields that are the same things. So the other piece of this that I've based a lot of this talk on is called Google Dapper. This is kind of a funny story. So I wanted to put a link to the Dapper paper in my slides, and I thought, maybe somebody has already made a short link for it. And so I went to bit.ly/Dapper. And it does not, in fact, go to the Google site, but it goes to this company called Hardgraft, which makes these awesome bags. And I have been looking for a bag like this for ages. And so I bought one, which I think probably is the best lead gen ever. I don't know. So Dapper itself, I did make a bit.ly that does not go to Hardgraft. So this is basically how Google does the things I've talked about. So some of the things were things that I kind of were based on the Google paper, specifically like the request traces and the things you can do with that. But a lot of the stuff with tracking your exceptions and tying them back to a request ID is stuff I've been thinking about for a long time. And they basically say all of the same things. They talk about a lot of the things that I talked about. They advocate storing their they call them connection IDs, but they store them in thread locals, so that way they're accessible across their entire request. For all their deferred calls, their async calls, in Google's case, as far as I can tell based on the paper, these are mostly background threads, not rescue type things, but they still use a consistent system for making those calls. They can then add that connection ID back into those, so they're always there. They have a consistent RPC framework that they use to make all of their backend calls across all of their different technologies. This works for Java, C++, and Python in their environment. And so they only had to instrument those 3 different RPC libraries to be able to get this across their whole system. They obviously operate at a much higher scale, but what I think is cool about this is that it proves that this kind of concept does work at that high scale. And they're not doing, obviously, request to log these exceptions out or log the requests out. They're just writing to a file, and they have daemons that pick it up and store it in Bigtable like everything else at Google. So back to our initial example. What's different this time? You still get paged at 4 in the morning. But now you don't have to know ahead of time the entire architecture of your system. You don't have to remember that at 4 in the morning. You can use the tools to help you diagnose what's going on. So let's say maybe you look at your front end, you look at all the exceptions that are coming in, you see that there's a ton of exceptions, but basically all of the exceptions are tied to a specific backend service. You look at that list of backend exceptions, and you see that all of those exceptions are basically coming from one box, and maybe even one process on that box. You can dive down into that box and see that maybe, for some reason, one of the processes has lost its connection to the database, but it's still serving requests, which is triggering a lot of failures. So if you didn't have this system, you would have to basically figure that all out yourself. But now, with this thing, the tool helps you figure that out and get there, which is pretty cool, I think. So again, this is all a work in progress. I think that these ideas are really cool. I'm working on getting them implemented so that way we can use them in Engineer, hopefully. But the important thing here is I think the status quo that we have for this kind of system is not enough. And I'd really like to see the community as a whole, including every company that I know of, to start doing this kind of thing, because I think it's pretty cool and it's pretty powerful. So thanks a lot. That's me.